has anyone ever heard of this term dilation, or maybe the verb dilate?
Yeah, like your eyes are like being dilated.
Okay, good. Yeah.
Really
No.
bright.
What's that?
Isn't like really bright and your eyes are dilated?
Yeah, that's good. So your eyes can dilate depending on how bright the light is, right? Noah, where have you heard dilate before?
Oh, same thing.
Same thing? Rashayla, same thing, or something different? Oh, my bad. Olamipo?
To dissolve into something else.
Ooh, to dissolve into something else? Interesting. Oh, that's dilute. Very close. But yes, great word association. I love that. Yeah, dilute would be like if I have a cup full of salt and I pour water in it, we're diluting the salt with water, that kind of thing. So yes, great. Dilation is a little bit different. Just like Kenny and a couple others said, your eyes are the main thing that you may know. Or, sorry, let me rephrase that. You may know dilation from eyes if you've ever been to the eye doctor. I know a lot of us are wearing glasses in here. You've definitely probably had your eyes dilated before. So a dilation refers to your pupils, right? If we're talking about an eyeball here, right? Here's an eye. And your pupil is the little black part right in the center of your eye, right? It's not really there, it's just a hole. That's why it's black. But that hole expands and shrinks to either let more light in or close more light out. Much like a camera, right? If any of you have ever used a camera, the shutter speed works the exact same way. It's closed, it opens up, lets some light in, and it closes again. That's how photos are taken. Your eyes do the same thing. If you're in a dark room and you let your eyes sit for a little bit, we might actually, if we have time, we'll do this. We'll do a little experiment here. But if you sit in the dark with your eyes open, what happens is your pupils dilate. They get a lot bigger, right? It will look something like that. Where this is a normal pupil, here's a dilated pupil. It's kind of scary, right? When you see it, it's a little freaky. But what your eyeball is doing there is it's opening up its frame of reference so that more light can come in because there's less light in the room. Now, if you go outside and you're in a really bright environment, your pupils will dilate in the opposite direction. They'll get a lot smaller. Because if they're open, if the dilation is large, you're letting way too much light in, you can go blind. So your pupils are basically just a regulator of the light in the space around you. Does that make a little bit of sense? Okay, Noah.
Is that what happens when you're in a dark room and you get used to the lighting so it gets a little bit lighter?
Exactly. That's exactly right. How many of you have ever been in your room and you turn off the lights and for like the first 5 minutes it's pitch black, you can't see anything, but then after a little bit of time you can start to see more outlines of stuff in your room and your eyes adjust to the light. You guys have probably heard that phrase. I see a lot of hands up. That's exactly what's happening here. So your eyes look like this, you turn the lights off. The pupils are so small that no light can come in, so you can't see anything. But eventually, those pupils enlarge or dilate and get larger, so you can let more of that visible light in. I'm not a science teacher, but hopefully that makes a little bit of sense. Ooh, interesting. If your pupils don't dilate, I would probably recommend seeing an optometrist, because that's not good. If your pupils cannot dilate themselves, I actually don't know. I don't know. That's a good question, though. That's a great question. I will look into it. But yeah, it's definitely not a normal thing for your pupils to not dilate. If we have time, we'll do a little experiment here where we turn the lights off and partner up. But anyway, let's get through these notes, and then we'll see if we have time for some fun. So, can someone read out the definition of a dilation for me real quick in math terms? Go ahead, Noah, and then we'll go Azalea for the next one.
A transformation that changes the size of a figure but not its shape to make the figure smaller or bigger.
Thank you very much, Noah. It's that simple. It's a transformation that changes the size of a figure but not its shape. Right? With those pupils up on the board. They're still circles, right? The shape didn't change, but the size of those circles is what changed. Azalea, thank you, Noah. Azalea, can you read out scale factor for us, please?
The degree to which a figure is enlarged or reduced.
Thank you very much. Scale factor is the degree to which a figure is enlarged or reduced. Enlarged meaning made bigger, reduced meaning made smaller. So it would be like if I say, wow, you grew to twice your height. The scale factor there would be 2, because that's the degree to which you were made larger or grew. If you say that like, oh, he's half your height, the scale factor there is 1/2. You guys see what I'm saying? Okay, well, hopefully we will in a little bit. Thank you for reading those both out. To dilate a figure. This transformation is different. We're not going to split it up into graphing one day and learning the rule the next day, because in order to graph it, you kind of have to use the rule. However, the rule is pretty simple. Here's what it is. All we have to do is multiply each coordinate, x and the y, by the scale factor that you're given. Okay? Like I said, if you know how to multiply, today's lesson will be a breeze. Let's take point J here. Or actually, I should say, let's take triangle JKL here. All right? Triangle JKL. We're going to dilate this figure by a scale factor of 2. So, does anyone want to take a guess? If we're dilating it by a scale factor of 2, are we going to make our triangle larger, or do you think we're going to make our triangle smaller? What do you guys think? Give me a thumbs up for larger. Give me a thumbs down for smaller. What do you think is going to happen here? I see mostly all thumbs up. That's a great prediction, okay? What about this tells you that maybe we're going to get a larger triangle here? Jordan, go for it.
The multiplication sign.
The multiplication sign. Good. That's great. That's a great start. Anyway, we'll get to that with example B. But yes, we are going to make this triangle larger. And we're going to do exactly what Jordan just said. We're going to multiply each of these 6 numbers here, all 6 of our coordinates, 3 x's, 3 y's. We're going to multiply all 6 of those numbers by our scale factor. If you have a highlighter, this might be a helpful time to use it. So, point J is at 1, 2. We're dilating this triangle by a scale factor of 2, meaning that we're making it twice as large. So we just have to multiply 1 and 2 by the scale factor of 2. What would my new coordinates for J prime here be? Anyone want to take a guess? Well, let me ask you this. What's 1 times 2? 2. What's 2 times 2? 4. There's our image coordinate right there. We took point 1, 2. We made it twice as big. Now it's 2, 4. Now let's go down to point K. 2 times 2. What's that going to give us for a new x coordinate? 4. What about negative 1 times 2? Negative 2, right? Now let's go down to L. What's negative 2 times positive 2? Negative 4, and 0 times 2 stays as a 0. That's absolutely right. There we go. We just dilated this triangle by a scale factor of 2. Not too bad, right? Hopefully. So before we look at example B, let's go ahead and graph this and see what it looks like. Take a look down at our first graph here, triangle JKL, corresponding to these coordinates up here in example A. And we're going to go ahead and plot our prime coordinates now. J prime is at 2, 4. Go over 2, up 4. There's J prime. K prime is at 4, negative 2. Over 4, down 2. There's K prime. And L prime is at negative 4, 0. So starting from the origin, we'll go to the left 4, and we'll go down 0. We're going to land right there on our x-axis, and we'll call that L prime. Go ahead and distribute the small plastic rulers that you have. If you don't have a ruler in front of you, connect all 3 of those points together, and we'll get our image figure. Our new triangle, J prime, K prime, L prime, is going to look just like this. I'll zoom in so we can all see. That's what we got. So let's think back to our prediction. A lot of you had your thumbs up predicting that our triangle was going to get larger when we dilate it by a scale factor of 2. Was that prediction correct, everybody?
Yes.
Yes, it sure was. Our orange triangle did get much larger than our original pre-image triangle. How much larger did it get? Twice as large, right? We multiplied every coordinate by a scale factor of 2. So this triangle, J prime, K prime, L prime, is twice as large as J, K, L. You don't have to write this after each problem, but I do want to put that in there for our notes. Now, we got the definition of dilation, I believe, from Noah. Changes the size of the figure, but not its shape. And in parentheses there, it says it makes a figure smaller or bigger. So we just made a figure bigger. Let's go ahead and make one smaller. Let's take a look at example B. We're going to dilate the figure MNO, or the triangle MNO, by a scale factor now of 1/2. Let's make another prediction. Thumbs up for larger, thumbs down for smaller. What do we think is going to happen with M prime, N prime, O prime? Are we going to get larger or are we going to get smaller? Smaller. That's right. I see all thumbs down. We are going to get smaller here. When we have a scale factor that is a fraction, our image triangle is going to be a fraction of the size, meaning it's going to get smaller. So if we're dilating by a scale factor of 1/2, all we have to do is multiply each coordinate by 1/2. You'll notice for convenience, all of our coordinates here are even, which is nice, because we can cut those in half fairly easily, right? Let's take a look at M prime. What would half of positive 4 be? Positive 2. Again, 4 times 1/2 gives us 2. Down to N prime. What's 0 times 1/2? 0. What about negative 4 times 1/2? Negative 2. Finally, we got O prime. Half of negative 4 is negative 2. And half of 4 is just 2. So it really does look like each of our coordinates got half as large. Technically, the coordinates themselves didn't get larger because the coordinates are just a point, but you guys hopefully know what I'm saying. Let's go ahead, take a look down here at example B's graph of triangle MNO, and let's plot our image coordinates. M prime is at 2, 2. So we'll go to the right 2, up 2, and call that M prime. N prime is at 0, negative 2. So we're not going to go left or right at all. We're just going to drop down 2 spaces and make our new dot there, N prime. Finally, we got O prime at negative 2, positive 2. So we're going to go left 2, up 2. There's O prime right there for you. Once again, using your ruler, we'll connect all 3 of those points to get a nice straight triangle here. Just like that. So what happened now here? Did our triangle get larger or did it get smaller? It got smaller, right? How much smaller? Well, m prime n prime o prime is half as large as m n o. In example A, we dilated our triangle by a scale factor of 2. We made it twice as big. In example B, we dilated our triangle by a scale factor of 1/2. We made it half as big. The shape of the triangle did not change at all. And technically, the position of the triangle didn't change at all either. Notice how whether we got a larger triangle or a smaller triangle, they're overlaid on top of each other nice and evenly. The reason why that is because we're dilating these figures about the origin, which is that phrase we learned the other day with, I think it was with rotations, where we rotate a triangle about the origin. Basically, it just means we're keeping everything centered. That's all that means. All right, what questions can I answer about these dilations? Like I said, the real work here is just multiplying each coordinate by the same number 6 times. That's essentially what we're doing in this lesson. Is multiplying each coordinate by the number that we're given. For example, if we look ahead to today's worksheet number 50. What a big milestone. Worksheet number 50. Hooray. We got only, it's 10 problems. It's not too bad. So you'll be given a dilation, or you'll be given a scale factor, I should say, of 5, scale factor of 2, scale factor of 2, 4, and then on the back you'll have some 1/2s. There's even a 2.5 thrown in there, all right? 0.5, all that good stuff. Here's what I'm going to want you to do. Before I get this passed out, I want to talk about what I want to see, just so we're all on the same page. So we got to identify the pre-image coordinates. I know this part is not great because it takes a little bit of work, but again, we can't dilate if we don't know what the coordinates are, because we need to multiply the coordinates by the scale factor. You see what I'm saying? So STU, we're going to write it out just like this. -1, 0, 0, -1, and t is at 1, 1. We're going to multiply each of these numbers by what? Oh, sorry, you can't see it. Sorry. By 5. We just take the scale factor and multiply each of these by 5. So -1, 0 becomes -5, 0. 1, 1 becomes 5, 5. And 0, -1 becomes 0, -5. So you plot all 3 of those points, label them, and draw your triangle. Now notice how with this one, number 1, I'll keep this up just so you guys can copy it down as we get started on this worksheet with the time that we have left, but we can see that we had a lot larger scale factor here, right? A scale factor of 5. And we can see that reflected in our dilation. The new triangle, our image triangle, is way larger than our pre-image triangle because we dilated it by a much larger scale factor. All right? So this is what I should see on your worksheets. Let's go ahead and get those to you, and we'll go from there.